Scientists studying one of the largest glaciers on the planet just said something that should make you stop scrolling. The wall of ice that has been holding back an entire section of Antarctica for decades is about to disappear, and researchers are calling it one of the clearest warning signs we've seen in years. Stick with me for the next few minutes, because by the end of this, you'll understand exactly why a floating slab of ice thousands of miles away could end up reshaping coastlines you actually live near. Let's start with the glacier itself, because most people have heard the nickname without really knowing what it refers to. Thwaites Glacier sits in West Antarctica, and it is enormous. We're talking about a river of ice roughly the size of Florida, stretching about 75 miles across at its widest point, and in places it's more than 6,500 feet thick. That's taller than most mountains you could name. People call it the Doomsday Glacier for a reason, and it's not just for dramatic effect. Thwaites isn't just one glacier sitting off on its own. It acts like a plug, or if you want a simpler picture, think of it as a cork holding back a much bigger bottle. Behind Thwaites sits the West Antarctic ice sheet, an ice mass so large that if it all eventually slid into the ocean, global sea levels would rise by more than 10 feet. Thwaites is one of the main things standing between that ice sheet and the open ocean. Pull the cork, and everything behind it starts moving faster. Now here's what just happened, and why scientists suddenly sound a lot more urgent than usual. In front of Thwaites, there's a floating extension of ice called the Eastern Ice Shelf. This isn't the glacier itself. It's a slab of ice that sits out over the water, attached to the front of the glacier, acting as a brace. Its entire job is to push back against the ice, trying to flow out from behind it, slowing the whole system down. For years, researchers have been watching this ice shelf weaken. Now, according to scientists with the British Antarctic Survey, that shelf is expected to break apart before the year is out. One of the lead researchers on the project, a marine geophysicist named Robert Larder, put it about as plainly as a scientist ever does. He said the last remaining piece of ice shelf in front of the glacier is on the edge of falling apart, and that while nobody knows exactly how it will happen, there is no real doubt that it's going to happen. That's a big deal, and here's why. Once that ice shelf is gone, the break is gone with it. The glacier behind it won't have anything physically pushing back against its flow into the sea. Satellite images already show this process starting. Huge cracks are opening up right where the shelf connects to an underwater ridge that has been anchoring it in place, and more fractures are appearing right where the ice shelf meets the front of the glacier itself. Those are the 2 points holding the whole structure together, and both are giving way at the same time. One researcher from the University of Innsbruck described watching the satellite footage and compared it to a car windshield shattering, where suddenly whole sections just start breaking into pieces rather than cracking slowly and predictably. If you want a number that actually shows how fast this is moving, look at the flow rate. Scientists tracking the ice shelf's movement found that its speed has roughly tripled between January 2020 and January of this year, now sitting at just over 2,000 meters annually. For context, that kind of acceleration in such a short window is not something researchers expected to see this soon. It tells you the ice isn't just cracking. It's actively speeding up, which is usually a sign that whatever structural support was holding it together is failing faster than the models predicted. So what happens next, realistically? Let's be clear about something right away, because it matters. Nobody is saying Antarctica is about to collapse overnight, and nobody is saying coastal cities are going to flood next year. A structure this size doesn't disappear in a news cycle. Full disintegration of a glacier like Thwaites would play out over centuries, not months. But here's the part that actually matters for anyone paying attention. Once that eastern ice shelf breaks away, the glacier behind it loses one of its last major forms of resistance. Ice that was previously being held back will start flowing into the ocean noticeably faster. And once ice starts moving briskly toward open water, it becomes very difficult to slow back down, because the ocean underneath is what's driving the melting in the first place. That brings us to the actual mechanism causing all of this, because it's easy to assume warm air is the main culprit, but that's not really the story here. The real driver is ocean water, not atmospheric temperature. Changes in wind patterns around the southern hemisphere have been pushing warmer water up from deeper parts of the ocean, and that water is sneaking in underneath the glacier, right where the ice meets bedrock below sea level. This is happening out of sight, underneath. Thousands of feet of ice, which is part of why it took so long for scientists to fully understand what was going on. The ice is essentially being eaten away from below while the surface looks relatively normal. Researchers have used an underwater robot called IceFin to send cameras down into the cracks and channels beneath the glacier, and what they found was startling. Warm water is funneling through fissures far more efficiently than expected. In some spots, it's been detected penetrating more than 6 miles beneath the ice, actively accelerating the melt from underneath. Here's something that might surprise you. This isn't actually a brand new problem that started last year or even in the last decade. Thwaites has been retreating steadily since the 1980s, and it's already pulled back roughly 12 miles from where it used to sit back in 1992. But newer research digging into the deeper history of the glacier found something even more interesting. Evidence suggests the retreat we're seeing today may have actually been set into motion back in the 1940s, likely triggered by a powerful El Niño event at the time. If that's accurate, it means this: glacier has essentially been on a slow, multi-decade collapse trajectory that started before most of our grandparents were even born, and we're only now watching the more dramatic phase of it play out in real time. That's a sobering thought, because it means whatever changes we make going forward may take just as long to show results, if they can meaningfully change the trajectory at all. Let's talk numbers, because these are the figures that actually matter if you want to understand the stakes here. If Thwaites Glacier alone were to fully melt, scientists estimate it would raise global sea levels by around 65 centimeters, or a little over 2 feet. That number alone would be enough to cause serious problems for low-lying coastal areas around the world. But Thwaites melting completely doesn't happen in isolation. Remember, it's the cork in the bottle. If Thwaites goes, it destabilizes the ice behind it, and that's where the numbers get genuinely alarming. The full West Antarctic ice sheet holds enough frozen water to raise global sea levels by more than 10 feet if it were lost entirely. Some individual scientists have put out even higher long-range estimates under worst-case emission scenarios, though there's real disagreement in the field about how fast and how far this could realistically go. What almost everyone studying this agrees on is that Thwaites is currently changing faster than earlier models predicted, and that alone is enough to take seriously. One recent study modeling the glacier's future found that by 2067, Thwaites could be shedding somewhere between 180 and 200 billion tons of ice every single year. To put that in perspective, that is an almost incomprehensible amount of mass moving off land and into the ocean annually, and that rate alone, sustained over time, would meaningfully contribute to global sea level rise well before the glacier is anywhere close to fully gone. This is part of why researchers describe ice sheet collapse as a tipping point rather than a gradual slope. Once certain thresholds are crossed, especially with warm water actively undercutting the ice from below, the process can become extremely difficult to reverse, potentially locking in changes that persist for thousands of years regardless of what emissions look like afterward. It's worth pointing out that scientists don't all agree on exactly how dramatic the worst-case scenario really is. Some computer models suggest that a sudden, rapid collapse driven by towering ice cliffs breaking off in massive chunks, a scenario some researchers have worried about in the past, might actually be less likely than originally feared. Other scientists studying the ocean conditions around Antarctica argue the opposite, pointing out that Thwaites has consistently outpaced earlier predictions and that current trends suggest we may be underestimating how quickly this could unfold. The honest answer is that there's still real uncertainty here. Glaciologists openly admit that modeling something this massive, with so many variables interacting at once, deep ocean currents, wind patterns, bedrock topography, ice fracture mechanics, is extraordinarily difficult. What almost nobody disputes anymore is the direction things are heading. The disagreement is mostly about speed and scale, not about whether Thwaites is destabilizing. There's also a broader piece of this story that doesn't get talked about enough, and that's what's happening to the sea ice surrounding Antarctica as a whole. Separate research looking at ocean conditions around the continent found that deep, trapped heat in the Southern Ocean has been rising toward the surface in a way that wasn't fully understood before, and that this shift is contributing to unusually low sea ice levels around Antarctica in recent years. At one point, an area of missing winter sea ice roughly the size of Texas simply wasn't there when it normally would have been. That's not directly the same story as Thwaites, but it paints a picture of a broader system under stress, where multiple pieces of Antarctica's ice are behaving in ways that don't match historical patterns. So, what does all of this actually mean for you, sitting wherever you're watching this from? If you don't live directly on a coastline, it's tempting to file this under someone else's problem. But sea level rise doesn't stay contained to Antarctica or to the specific coastal towns nearest the equator. Cities like Miami, London, and countless low-lying regions across places like Bangladesh and the Pacific Islands are all named repeatedly by researchers as areas of serious long-term concern. Even a rise of 2 feet, which is on the more conservative end of what's being discussed here, is enough to dramatically increase flooding during storms, push saltwater further into freshwater systems, and force costly infrastructure changes in major coastal cities over the coming decades. And that's before you factor in what happens if the wider West Antarctic ice sheet destabilizes behind it. To be fair to the science, and to avoid making this sound more immediate than it is, none of this means beaches are vanishing next summer. The researchers themselves are careful to say this unfolds over decades and centuries, not overnight. The ice shelf breaking apart this year is a milestone, not a doomsday clock hitting zero. But it is a milestone that removes one of the last mechanical safeguards, slowing this glacier down. And once that happens, the pace of change tends to accelerate rather than plateau. That's exactly why researchers are treating it as such a significant moment. It's less about what happens this year and more about what this year sets in motion for the years and decades that follow. It's also worth mentioning just how difficult and dangerous this research actually is to conduct. Earlier this year, a team of scientists and engineers tried to set up camp directly on the rapidly shifting ice shelf, hoping to plant long-term monitoring equipment beneath the glacier itself. The environment out there is brutal and unpredictable, and despite serious effort, the team wasn't able to get that equipment fully installed the way they'd planned. Even so, they managed to gather valuable readings from underneath the glacier's main trunk, and what they found lines up with everything else we've covered here. Water beneath the ice moving faster and warmer than earlier estimates suggested. Researchers monitoring this region have said they're now checking satellite data on the ice shelf daily, which tells you how seriously the scientific community is treating this specific moment. If there's one thing to take away from all of this, it's that Thwaites has become a genuine bellwether for how fast climate systems can shift once they start crossing certain thresholds. This glacier has been retreating for decades, quietly, out of sight, in one of the most remote and hostile places on Earth. Most people never thought about it because it didn't feel urgent. That's changing now, not because of speculation, but because researchers are watching real structural failure happen in close to real time through satellite imagery and physical measurements. The eastern ice shelf breaking apart this year removes a support system that's been holding back a much larger and more consequential mass of ice, and while nobody can tell you the exact date coastlines will look meaningfully different, the trajectory is no longer really in question among the people who study this for a living. Let's zoom out for a second and talk about who's actually doing this research, because it helps explain why we're getting such detailed information about a glacier sitting in one of the most remote places on the planet. Since 2018, an international group of scientists from the US and UK have been running a joint program called the International Thwaites Glacier Collaboration. This isn't a handful of researchers working off satellite images from an office. It's a large coordinated effort involving ice-breaking ships, underwater robots, GPS sensors drilled into the ice, and teams willing to camp directly on one of the most unstable and dangerous surfaces on Earth to gather direct measurements. That's a serious level of investment, and it tells you how important the scientific community considers this particular glacier to be. Thwaites isn't just one glacier among thousands in Antarctica that happens to have a scary nickname. It's been treated as a priority research target for years, precisely because of what sits behind it. And one of the researchers involved in this collaboration, a glaciologist named Eric Rigno from the University of California, Irvine, has been fairly open about how much uncertainty is still baked into this whole picture. Even with all this data, all these instruments, and years of monitoring, scientists still can't give you an exact date for when major thresholds will be crossed. What they can tell you is the direction things are moving, and that direction has consistently been toward faster change, not slower. That distinction matters a lot when you're trying to understand headlines like this one. This isn't a case of scientists guessing wildly or exaggerating for attention. It's a case of real uncertainty about timing, layered on top of very high confidence about the overall trend. It also helps to understand what's physically happening at what scientists call the grounding line. Because this term comes up constantly in glacier research, and it's honestly not that complicated once you picture it. The grounding line is simply the point where the glacier stops sitting directly on solid rock and starts floating on the ocean instead. For a lot of Thwaites, that grounding line sits below sea level, which is a problem because it means warm ocean water can physically reach underneath the ice at that point rather than being blocked by higher ground. As the ice melts from below, the grounding line itself retreats further inland, exposing even more of the glacier's underside to that same warm water. This creates a feedback loop. More exposure leads to more melting, which leads to more retreat, which leads to even more exposure. Once that loop gets going in an area where the bedrock underneath continues sloping downward inland, which happens to be the case for large sections of Thwaites, there's genuine concern among researchers that the process could become extremely difficult to slow down using anything short of a major shift in ocean temperatures. It's also worth putting Thwaites in context alongside its neighbor, Pine Island Glacier, since the two are often mentioned together in Antarctic research. Pine Island sits right next to Thwaites and has been going through a similar pattern of accelerated melting and retreat over the past few decades. The reason researchers usually talk about them as a pair is that they act as two connected pressure points, holding back the same broader section of the West Antarctic ice sheet. If one destabilizes significantly, it doesn't just affect that glacier in isolation, it changes the stress and ice flow dynamics on the other one too. That's part of why scientists are cautious about treating Thwaites as an isolated news story. What happens here has ripple effects across a wider network of ice that's all connected underneath the surface. Now, here's a fair question worth addressing directly. If this process takes centuries to fully play out, why does a single ice shelf breaking apart this year deserve this much attention right now? The honest answer is that milestones like this one function as checkpoints. They're moments where scientists can compare what's actually happening against what their models predicted years earlier. And in this case, the ice shelf breaking up now, faster and more chaotically than some earlier projections expected, is itself useful information. It suggests that current models may need to be adjusted to account for faster structural failure than previously assumed. That has real consequences, because sea level projections used by coastal cities for infrastructure planning, flood defense budgets, and insurance risk models are all built on these same glacier models. If Thwaites is moving faster than expected, some of those planning assumptions may need to be revisited sooner than governments and engineers were originally expecting. There's a reasonable comparison here to something like a structural engineer inspecting a bridge. A bridge doesn't collapse the moment engineers spot the first crack in a support beam. But when a crack that was supposed to develop slowly over decades suddenly starts spreading rapidly within a few years, engineers don't wait around to see what happens next. They treat it as an urgent signal that something in their original assessment needs updating. That's essentially the situation with Thwaites right now. The eastern ice shelf isn't the whole structure, but it's a critical support piece, and it's failing faster than the original timeline suggested it would. So where does that leave things practically? For coastal regions, especially places already dealing with regular flooding during storms or high tides, this kind of research reinforces the importance of long-term planning rather than reacting only after damage happens. For everyone else, even those living nowhere near an ocean, it's worth understanding that events like this tend to have consequences that show up gradually through things like higher insurance costs in coastal areas, shifting agricultural patterns, and increased migration pressure in vulnerable coastal nations over the coming decades. This isn't the kind of story where you wake up one day and the world looks dramatically different. It's the kind of story that quietly reshapes decisions being made right now by engineers, city planners, and insurance companies who are paying very close attention to exactly the kind of research we just walked through. I'll be keeping an eye on this story as it develops, because this is exactly the kind of event that tends to produce new findings over the following weeks and months, as researchers get a clearer look at how the ice shelf actually breaks apart and how quickly the glacier behind it responds. If new satellite data or a new study comes out, I'll bring you a proper update the moment there's something worth reporting. If stories like this matter to you, go ahead and subscribe, because I cover developments like this regularly, and this is very likely not the last update we'll see on Thwaites this year. Thanks for watching, and I'll see you in the next one.